Next, Dirac delta function or delta distribution or unit impulse. So definition, it is defined as a generalized function which is zero everywhere except at 0 and whose integral over the entire real line is equal to 1. Entire real lines means minus infinite to plus infinite. Minus infinite to plus infinite, delta t dt equal to 1. That is what. So mathematically, in usual sense, it is not a function. Normally, because it is not well defined at t is equal to 0, equal to infinite. So that is what mathematically is not a function, but we used to call this function as a Dirac delta function, right? For our convenience, right? For understanding. So some properties, that is what, and minus infinite to plus infinite, delta d dt equal to 1. Suppose f of t is a well defined function, then integral minus infinite to plus infinite, delta t minus a f of t dt is equal to f of a. Some useful results. Also it is defined as integral a minus epsilon to a plus epsilon delta t minus a f of t dt is equal to f of a for any epsilon greater than 0. Some properties of delta function. First, delta t is an even function. Delta t is equal to delta minus t. Then delta of a t is equal to 1 by modulus a delta t. A is non-zero number or constant. F of t delta t minus a, which is equal to f of a delta t minus a. Then integral delta t minus x into delta x minus a into dx is equal to delta t minus a. Then delta omega, which is equal to 1 by 2 pi integral minus infinite to plus infinite e power minus I omega t d omega. This is Fourier transform of del. Then the time domain impulse can be represented by delta t, which is equal to 1 by 2 pi integral minus infinite to plus infinite e power I omega t dt. Right? So we will see the next problem. Xt is a constant random process with r of tau, which is equal to m square for all tau, where m is a constant. Show that the spectral density of the process is s omega, which is equal to 2 pi m square del omega. Given r of tau, which is equal to m square, right? Then spectral density s omega is equal to Fourier transform of r of tau, which is equal to minus infinite to plus infinite m square e power I omega tau d tau. So m square constant, taking m square outside the integral. So m square integral minus infinite to plus infinite e power I minus I omega tau d tau m square. So by the results and delta function, delta omega, which is equal to 1 by 2 pi integral minus infinite to plus infinite e power I omega tau d tau. That means integral minus infinite to plus infinite e power I omega tau d tau is equal to 2 pi delta omega. So we are replacing that one. So m square into 2 pi del omega. That's all. Next problem. Find the PSD of random process x of t f r x x of tau is equal to 1 plus e power minus alpha modulus tau. So we need to find the power spectral density. So given r of x is equal to r of tau, which is equal to 1 plus e power minus alpha modulus tau, equation number 1. Spectral density is nothing but Fourier transform of r, so which is equal to integral minus r of tau e power minus omega tau d tau, replacing r of tau integral minus tau to minus infinite to plus infinite 1 plus e power minus alpha modulus tau e power I omega tau. So which is equal to integral minus infinite to plus infinite e power minus I omega tau d tau plus integral minus infinite to plus infinite e power minus I omega tau e power minus alpha modulus tau d tau. We are splitting the integral into 2 because 1 plus e power minus alpha modulus tau. So multiplying with e power I omega tau, right? So 1 into e power I omega tau d tau, first integrand. Second one, e power minus alpha modulus tau into e power minus I omega tau, that is the second integrand. So we know the value of the first integral, 2 pi del omega, plus integral minus infinite to plus infinite, e power minus I omega tau into e power minus alpha modulus tau d tau. So first term is 2 pi del omega, plus we are splitting into 2. So first negative term, negative part of the integral, so minus infinite to 0 e power minus I omega tau. So modulus tau become minus tau in the negative part. So e power minus alpha minus tau d tau, plus positive part 0 to infinite e power I omega tau e power minus alpha modulus tau become tau in the positive part into tau d tau, right? So we are grouping the e powers. So 2 pi del omega plus minus infinite to 0 integral e power alpha minus I omega, tau is constant, sorry, common, so take it outside, into d tau, plus integral 0 to infinite e power minus alpha I omega into tau d tau. Now we can use e power ax, integral e power ax is equal to e power ax by a. So you are using that formula. So 2 pi del omega plus e power a minus I omega tau by a minus I omega. Here instead of a we are having a minus I omega, right? E power ax, integral e power ax, right? So similarly the second one, plus e power minus alpha plus I omega tau by minus alpha plus I omega, limit is 0 to infinite. Applying the limit, so 2 pi del omega plus e power first term upper limit 0, so instead of tau we are putting 0, so e power 0 by alpha minus I omega minus e power minus infinite lower limit alpha minus I omega, plus next integral e power minus alpha plus I omega upper limit infinite by minus alpha plus I omega minus lower limit 0 e power minus alpha plus I omega into 0 by minus alpha plus I omega. E power minus infinite 0 we know, so 2 pi del omega 1 by alpha plus I omega, e power 0 1, plus 0 minus 1 by minus alpha plus I omega. Grouping this, so you will get 2 pi del omega, the minus into minus, plus 1 by alpha minus I omega 1 by plus 1 by alpha plus I omega. So taking LCM and solving, alpha plus I omega plus alpha minus I omega minus I omega get cancelled, 2 alpha. So 2 pi del omega 2 alpha by in the denominator a minus b into a plus b, a square minus b square, so alpha square minus I omega square. I square is minus 1 again, so minus into minus plus alpha square by omega square, right, in the denominator. So therefore s omega, which is equal to 2 pi del omega plus 2 alpha by alpha square plus omega square. Thanks. I'll see you in the next video.